Fetching the first 10 rows takes 1 millisecond, while fetching the same 10 rows at page 1000 takes 5 seconds. This geometric performance degradation occurs because the database engine must scan and discard every preceding row before reaching your target offset. The select statement combined with limit and offset is the standard approach for pagination in most application frameworks. Developers implement this because it is simple to write and supported by almost every relational database system, including PostgreSQL and MySQL. When you request an offset of 10,000, the database does not jump to that position. It must retrieve 10,010 rows from the storage engine, sort them if an order by clause exists, and then throw away the first 10,000. The computational complexity of offset pagination is big O of n. As your dataset grows or the user navigates deeper into the results, the execution time increases linearly with the offset value. This creates a ticking time bomb for large-scale production databases. Even with an index on the sorting column, the database cannot skip rows efficiently. B-tree indexes are designed for finding a specific value or a range of values, but they do not store the relative position of rows within the sorted set. To reach the specified offset, the database performs an index scan. It visits each index entry and increments an internal counter until it reaches the target. This process consumes central processing unit cycles and memory bandwidth for data that will never be used. Deep pagination causes buffer pool pollution. To scan through the rows, the database must load data pages from the disk into the memory. This evicts frequently accessed data from the cache, which forces other queries to perform slow physical disk reads. If the index does not fit in memory, the database performs random disk access to read index pages. At high offsets, this results in thousands of small read operations, which can saturate the storage throughput and lead to application-wide latency spikes. Offset pagination is fundamentally broken for dynamic data. If a new row is inserted at the beginning of the list while a user is navigating, all subsequent rows shift down by one. This causes the user to see a duplicate entry on page 2. Conversely, if a row is deleted from a previous page, the results shift up. When the user clicks Next, they will skip a row entirely without ever seeing it. This lack of consistency makes offset pagination unsuitable for real-time activity feeds. The solution is Keyset pagination, also known as the seek method. Instead of telling the database how many rows to skip, you tell it exactly where to start reading based on the last value seen in the previous result set. A Keyset query uses a where clause to filter out rows. If you are sorting by primary key, your query becomes select where ID is greater than the last ID from the previous page, limit 10. This allows the engine to use a direct index seek. An index seek has a logarithmic complexity of big O of log n. The database traverses the B-tree height and finds the starting point instantly. It then reads exactly the number of rows requested and stops immediately, avoiding any wasteful scanning. With the seek method, the performance remains constant regardless of the page depth. Whether you are on page 1 or page 1 million, the query time is essentially the same. This stability is critical for maintaining predictable response times in high-traffic applications. Keyset pagination solves the data drift problem. Because the query is tied to a specific value rather than a relative position, insertions and deletions on previous pages do not affect the starting point of the next page. The pagination remains stable and accurate. Modern application programming interfaces prefer statelessness. Offset pagination forces the database to behave as if it has state, while Keyset pagination leverages the data itself to define the state. This makes it much easier to implement across distributed microservices and load-balanced environments. Implementation becomes more complex when sorting by non-unique columns, like timestamps. To ensure a deterministic order, you must include a unique column, like the primary key, in your sort order. This creates a composite key set that uniquely identifies every row in the set. To filter using a composite key set, you use a row constructor or a nested logic check. In SQL, this looks like where timestamp is less than last timestamp, or timestamp equals last timestamp, and ID is greater than last ID. This ensures precise positioning. Postgres and MySQL support row value expressions, which simplify composite filters. You can write where the pair of timestamp and ID is greater than the pair of last values. The database optimizes this syntax into an efficient index seek across multiple columns. To make the seek method fast, you must create a composite index that matches your sort order. For a sort on timestamp and ID, An index on both columns in that specific order allows the database to locate the starting point without any sorting overhead. The main limitation of Keyset pagination is that users cannot jump to an arbitrary page like page 500. They can only navigate to the next or previous page. For most modern user interfaces, like infinite scroll, this is a perfectly acceptable trade-off. Infinite scroll is the primary use case for Keyset pagination. Mobile applications benefit significantly because the seek method provides a smoother user experience with no loading delays as the user scrolls deeper into long lists of content or social media updates. To implement a previous page button, you simply reverse the sort order and the comparison operator. If your next page query uses greater than and ascending order, the previous page query will use less than and descending order to find the preceding set of rows. Users often expect to see a total count of results. However, running a count star query on a large table is just as expensive as offset pagination. For massive datasets, consider providing an estimated count from table statistics or omitting the count entirely. If exact counts are mandatory, cache the result for a few minutes. Alternatively, store the count in a separate metadata table that is updated via triggers or application logic. This prevents every pagination request from triggering a full table scan for the count. When designing your application programming interface, return an opaque cursor string instead of raw values. This string can be a base64 encoded version of the Keyset values. This abstracts the implementation details and allows you to change pagination strategies later. If the row referenced by your cursor is deleted, the seek method still works correctly. The greater than filter will simply pick up at the next available row in the index. This robustness is a major advantage over offset, which would cause a skip. Always include a limit clause, even with Keyset pagination. The limit tells the database optimizer to stop the scan as soon as the required number of rows are found. Without it, the database might scan the entire remainder of the index. Analyze your execution plans using the explain analyze command. Look for index seek or index scan operations. If you see a sort operation or a temporary table on disk, it means your index is not properly covering the pagination requirements. Be careful with complex types in Postgres. Some types, like network addresses or generic JSON objects, may not support the necessary comparison operators for Keyset pagination. Stick to primitive types like integers and timestamps for your pagination keys whenever possible. MySQL can sometimes be optimized with a technique called late row lookups. You first fetch the primary keys using the offset, then join back to the main table to get the full rows. This reduces the amount of ADA the engine must process. Even with late row lookups, the database still has to count the offset. It is a mitigation, not a cure. The seek method remains the superior choice for any system that expects to scale beyond a few thousand rows of data. Keyset pagination shifts some complexity to the application layer. Your code must keep track of the last value and construct the next query. However, this small investment in code quality results in a massive gain in database stability and performance. Many modern frameworks like Ruby on Rails or Django now have libraries that automate Keyset pagination. Search for cursor-based pagination plugins to avoid writing the complex SQL logic manually while still reaping the performance benefits of the seek method. If you are migrating a legacy system, start by adding a unique index to your sorting columns. Then, gradually update your API endpoints to accept an optional cursor parameter. You can support both methods simultaneously during the transition period to ensure backward compatibility. In a table with 10 million rows, an offset of 5 million might take several seconds. The equivalent Keyset query will take less than 10 milliseconds. That is a performance increase of over 200 times just by changing the way you query. The input-output throughput saved by using Keyset pagination can be reallocated to other critical database tasks, like writes and complex reporting queries. This lowers your infrastructure costs by allowing you to run on smaller virtual machine instances or database clusters. For the first page of results, the cursor is null. Your application logic should handle this by omitting the where clause for the initial request. Every subsequent request will then include the cursor values returned by the previous database call. Because you cannot jump to specific pages, your user interface should reflect this. Use load more buttons or infinite scrolling lists. If you must show page numbers, consider only showing a few pages ahead and fetching the total count asynchronously. The seek method is not limited to relational databases. Distributed document stores like MongoDB and DynamoDB also suffer from offset performance issues and provide similar cursor-based mechanisms to iterate through large result sets efficiently. In summary, offset pagination is a scalability trap. It wastes resources, provides inconsistent results under load, and eventually kills database performance. Transitioning to Keyset pagination ensures your application remains fast and reliable as your data grows to millions of records. Your final step is to audit your existing slow queries. Look for the combination of large offsets and high execution times in your slow query logs. Replace them with the seek method and watch your database load drop immediately.